This is MATHguide.com, and my name is Mark Karadimos. In this video, we're going to test relations for symmetry. In our first section, we're going to discuss what it is symmetry means. In our second section, we're actually going to talk about the rules for testing for symmetry. In section 3, we'll go over an example, and in section 4, we'll go over a second example. All right, let's get started. In our first section, we're going to talk about symmetry in general. There are several different types of symmetries. There's reflectional, rotational, and point symmetry. But let's talk about symmetry as it applies to pictures. So in our first picture, let's take a look at a butterfly. So here's a picture of a monarch butterfly. So the first type of symmetry we should look at is horizontal symmetry. So if we were to make a horizontal line and draw that and compare it from top to bottom, we would notice that this figure does not have symmetry. In that we mean the top and the bottom do not have this reflectional property where they look the same. All right, however, if we were to look at a vertical line and we were to look at symmetry, we would see that the left side of the butterfly looks almost exactly like the right side. Matter of fact, we would have to look very closely at this picture to see that it doesn't exactly match. So we would say that a monarch butterfly has symmetry across its vertical axis. Let's take a look at a different shape. Since we're going to be looking at more mathematical shapes, let's put a mathematical figure up here. This figure is called a hyperbola, and if we look at the horizontal axis, we could see that the top and bottom of this hyperbola does have symmetry. The top and bottom look the same. Let's take a look at our vertical symmetry. So if we were to draw a vertical line through its axis, a vertical axis, we would see that the left and the right side look the same, so we would say it has vertical symmetry. Let's take a look at another shape. Here's another type of hyperbola. This hyperbola is in the first quadrant and the third quadrant. So we got the first quadrant, we got the third quadrant, and it's got some different properties. For instance, if we were to draw a horizontal line across the x-axis, we would see that the top and bottom do not look like they're the same. They do not have the exact reflectional quality. This part up here does not have its counterpart down here. Likewise, this branch over here is not represented up here. So we'd say that this does not have symmetry across the x-axis. Let's look across the y-axis, otherwise known as a vertical line. We'll notice here that it does also not have reflectional quality across there. This curve here is not represented across on this side. Okay, so it does not have symmetry across the y-axis. However, if we draw a diagonal line called y equals x, you'll notice that it does have symmetry across this diagonal line. You could see that we have this shape here on this side, which is matched perfectly here, and the same thing's true for down here. This branch here is matched perfectly across on this side. If we also draw the line y equals negative x, you'll see that it also has symmetry for the same reason. So different curves have different types of symmetry. However, this curve does have a different type of symmetry called symmetry across the origin. So on the origin, I'm going to put this blue dot. If I were to take a point on the curve, like let's say I'll take this point right over here, very close to the y, it has a y value of 4 and a very small x value. If I were to flip this point over the origin, it would land on itself. In other words, the other second part of the curve. If I were to take this point over here, flip it over the origin, it would land on itself also. And this is true for any point on the red curve. If you flip it over the blue point, it will land on itself on the other part, in the second part of the curve. So it has something called symmetry across the origin. In our next section, we'll actually show the mathematical tests for symmetry. Okay, section 2, what we're going to do is talk about the tests for symmetry. So there are 4 tests. Let's talk about the first test. The first test is to test to see if the relation has symmetry across the x-axis. So to test, what we do is we want to see if the top looks exactly like the bottom. So you want to see if the positive y values look like the negative y values. So we're going to replace the y with negative y. All right, let's talk about our second test. So if we want to see if the relation has symmetry across the line, that is the y-axis, we want to see if the right side looks like the left side. So we are going to replace the x values with negative x. Okay, and we'll simplify it and we'll see how that goes with the example. All right, there's another test we look for, and that is for the line y equals x. So for the line y equals x, we replace y and x. And as a matter of fact, we actually switch x and y. So wherever the y is, we replace it with the x. Wherever the x is, we replace it with the y. That's how that test works. Okay, and then for the last test, for the origin, if we want to see if it has this point reflection, this reflection across the point, the origin, we replace the x with negative x, and we replace the y with negative y. Now this does make sense, because if we imagine that we had a point over here, let's say this is 3, 1, and we wanted to see if we flipped it over the x-axis, because let's say this is actually a point on the curve, this unknown relation, if it rotates over the x-axis, in other words, if we flip it over the x-axis, it's supposed to be also over here on the curve, which would be -3, -1. So you'll notice that we are changing the x value from a +3 to a -3, and we're changing the y value from 1 to -1. So the x gets replaced with negative x, the y gets replaced with negative y. Okay, and it works, because if this is 2, 3, and over here it would be -2, -3. Anyway, that's how the test works. You replace x with negative x, y with negative y. Okay, that's how the 4 tests work. Let's actually give them a whirl for our next section. For our first example, we're going to determine if this relation passes any of these 4 tests. So I've got x squared plus xy equals 5. We're going to see if it has x-axis symmetry, y-axis symmetry, symmetry across the line y equals x, and of course the origin. Now here's some facts that we're going to be using here. We're going to say that if you square a negative, it's the same thing as having no negative at all, because a negative squared is a positive. If you take the absolute value of a value, it doesn't matter if it's a negative or a positive, you're going to get the same value. So these little tips are going to help us as we go through, as you will see. Okay, let's test the x-axis. If you want to determine if this relation has symmetry across the x-axis, you replace the y with negative y. Okay, so here's the original problem, and I'm replacing the y with negative y. Okay, so what happens when I multiply a negative times a positive? I get a negative. So now you compare this to the original problem, and you'll notice that they do not look exactly the same. The original has a plus here, it has a plus xy, and this has a negative xy. So note, this curve does not have symmetry across the the line x, the line which is the x-axis. All right, let's try the y-axis. So the test for the y-axis is to replace x with negative x. Okay, so we go into the original problem. Let's clean that up a little. We put in, we're going to put in negative x for x. Oops. Okay, so now we're going to square this. We'll take negative x and square it, so that means negative x times negative x is x squared. A negative times a positive is negative xy. Okay, so again, we notice that this curve does not look like the original. Here I've got a plus. This is a minus. This curve does not have symmetry across the line y equals x. Okay, let's try the line y equals x. Okay, what's the strategy for that? Well, our strategy is to replace and actually switch x and y. So instead of it being x squared, we're going to put y squared. And instead of xy, we're going to put yx. Okay, so you can see that I just swapped x's with y's. Now, you can see that I've got a yx. Now, technically, I can multiply in any order. So xy is the same as yx. However, this has a y squared, and the original has an x squared. There's no changing that, and there's no way that these two are equivalent to each other. So nope. This curve has no symmetry across the line y equals x. Let's test to see if the origin has symmetry. So let's see if when I do this problem, I replace the x with negative x. I replace the x with negative x, the y with negative y. Oop, and I think I could just squeeze that in there. Okay, so what happens when I square a negative? I get x squared. When I multiply a negative times a negative, I get a positive. Okay, so now I compare this to the original, and I would say, yep, it looks exactly the same. So this curve has symmetry across the origin, and that's it. It has no other type of symmetry that we've tested. Okay, let's go on to a second example. So here's our second example. Now we're going to take a look at a different curve. Now, this curve, unlike the last one, this one's really hard to graph. It would be very difficult for us to graph this. So sometimes there's a lot of advantage to figuring out the symmetry, because knowing the symmetry ahead of time, it demands less of us to graph. Maybe we only need to graph the curve in the first quadrant, and then we would know what the other quadrants are going to look like. So symmetry can come in handy for speeding up the graphing process. All right, let's go through all the tests. So how do we test for the x-axis? We replace the y with negative y. Okay, so I'm going through, and I'm going to replace the y with negative y. So anytime there's a y, it gets replaced with negative y. And we play cleanup. So according to our handy-dandy little sheet here, we know that, or our little checklist here, we could see that if you have a minus inside the absolute value, like this minus y, it's the same thing. It's going to have the same value as just the absolute value of y. And when I multiply a positive times a negative, I get a negative. Okay, now I compare this to the original. I'd say it looks really close, except I've got a negative xy, and our original has a positive xy, so I'd say no, no deal. This one does not have any symmetry with the x-axis. All right, let's try the y-axis. So for the y-axis, we replace the x with negative x. Well, I forgot to put the negative in there. Okay. Okay. So what happens here? Again, I've got a minus inside. That's like having no minus inside. A negative times a positive is a negative. And this looks exactly like the last one. So it's not exact match. So I've got a negative here, I got a positive there. It is definitely not a match. So I know that this has no symmetry across the line, which is the y-axis. All right, how do you do the test for the line y equals x? Well, you swap the x's and y's. So this is going to be absolute value of y, absolute value of x, and I'm going to swap these guys, so that's yx. Okay, now I could add in any order. 5 plus 2, 2 plus 5, they're the same. So I really, mathematically, I could switch these back around again. I could add them in that order. And I can multiply any order. 7 times 3 is the same thing as 3 times 7, so I can actually switch these back again because mathematically they're the same. Now I compare this to the original. I say, yeah, it's an exact match. So this relation does have symmetry across this diagonal line y equals x. All right, how do we test for the origin? We replace all the letters with their opposite. So that's a negative x, negative y, negative x, negative y. Hopefully I squeezed that one in there. Okay, so according to our sheet, if you have a negative underneath, or within, I should say, the absolute value, it's like not having it there at all. Okay, same thing for this one. If I multiply a negative times a negative, I get a positive. I compare this to the original, and I'd say, yep, it matches perfectly. So this relation has symmetry across the origin. It has point symmetry. So each of these relations have different properties and they have different checks. And it is possible to have these two work and those two not. It's possible to have none of them work. It's possible they have all of them work, like in the case of a circle. So depending on the relationship you're given depends on what these answers are. There's no shortcut. You have to go through these checks. All right, that's all there is to checking for symmetry. So go back to MATHguide.com, check out our interactive quizzes, instructional videos, and text-based lessons. Take care.